All right, this graph is a scatter plot with a couple of lines superimposed. And these lines come from the information that we have out of our Stata regression output. We have all of these scatter plot points. This shows the actual height and weight. And then what these lines show are the predicted values that we get if we use those equations. So these are just, these lines are just plotted equations. And this one shows the predicted weight for men along all these different height values. And then this one shows the relationship between height and weight for women. And you can see that these are not the same. These slopes are not, the slopes of these lines are not the same, which means that the marginal effect of height on weight differs by gender, which corresponds to the different coefficients that we saw coming out of those two models in this slide. So now I'm going to show you one other thing that you can do with regression modeling. You can also, given that we ran that model that had both height and age in it, we can also take a look at how weight varies over age. So note the change in the x-axis here. This used to be height, and now we've changed it to age. And in order to look at how age changes, we're freezing a couple of values. So let's just say we want to look at the relationship between age and weight, and we're going to do that for men who are 6 feet tall and women who are 5.5 feet tall. So this scatter plot, each one of these dots represents one person. It shows their age and the relationship with weight. So ignoring these other two lines here, just look at the general picture of all these dots. Not a real strong relationship, and that will correspond to relatively small coefficient estimates for age in the model. But it's interesting to note that there could be some differences across gender. Obviously, the male bar is higher than the women's one, and that corresponds to the fact that men generally weigh more at every age compared to women. So let's just start with women here. So what does this line represent? It means that at this point, so let's take a woman who is, and of course this entire red line on the bottom here is all 5'5", or women who are 5.5 feet tall. So if that woman is 30 years old, we would predict, knowing nothing else about her except for that she's 5.5 feet tall and 30 years old, we would predict that she weighs about, whatever this comes out to, maybe 157 pounds or something like that. And then over here, if we knew that she were 65 years old and holding constant that she's 5.5 feet tall, we would guess that her weight would be, it looks like it's just a little bit bigger, a little bit higher, maybe, 167 pounds, something like that. So that's just one other thing that you can do with multivariate regression. I want to just be really clear about what these lines represent. They're predicted weights that come from the regression modeling that we do. So let's just take this spot here. We looked at this one for women. Now let's look at this one for men. So this point on this graph, on this line, represents the predicted weight for a 6-foot man who is 30 years old. And the way that you get this number, this predicted weight, is you plug in all of the information that we know about them. So, and then we multiply by each of the coefficients. That's how you do a prediction using multivariate regression. So out of the model, we had this negative 21.56. Let me just quickly back up and show you this. So this negative 21.56 was the coefficient for height. 0.19 was the coefficient for height squared. And so on and so forth. And we can't forget about our constant term, which is 730 in the male model. Did not mean to make a reference to Zoolander right there. Okay, so we've got our coefficient on height, and we know that the value for this person, 6 feet tall, we put 72 here. So we plug that in. Now we plug in 72 squared here, and we multiply by the coefficient on height squared. We multiply the coefficient of age, which is about 1.679, times their age, which we know to be 30. We put 30 squared in for the age squared term, and we include the coefficient there. And then we don't forget about our constant term, which is 730.455. So if you take a calculator and you plug all of that in, you get a value of 197.9. So take a look at this graph. Bada bing, bada boom. That is pretty darn close to 197.9. Matter of fact, it's exactly 197.9. So that's what these lines mean.